Good morning. I'm going to present the paper Benign and Malignant Cancer Prediction using Deep Learning and Generating Pathologist Diagnostic Report. We have 8 authors who have collaboratively worked together to make this research possible. The 8 authors include Dr. Kaliyappan, Dr. Vimal, Nitish, Vishagan, Mr. Vijay Bhaskar, Dr. Muthukumar, Mr. Balamurali, and Mr. Ramnath. So, coming to the abstract, let's dive deep into what we are cooking up here. Our research revolves around the power of deep learning, where we've got two major players on our team, the CNN and YOLO-V5 AI models. The goal is to set up the game in diagnosing colon and breast cancer by being laser focused on distinguishing the good guys from all bad guys in medical images. But that's not all. We are also on a mission to automate the generation of pathologist reports using AI. So, patients don't have to wait around for their diagnosis. Additionally, we are tossing linear regression models into the mix of histopathology image analysis to classify different cancer types. At the end of the day, our main aim is to make the lives of pathologists easier, ensuring they can provide timely and super accurate reports. And why does that matter? Well, it's all about helping patients make more informed decisions and, in the grand scheme of things, reducing the number of people affected by cancer. In the introduction, we will discuss by starting the question. So, why are we all doing this? Because cancer is a major player on global stage when it comes to public health. The traditional methods we have been using for diagnosis, like histopathology, are solid, but they take their sweet time and they need experts to read the results. That's where deep learning starts in. This tech uses algorithms that are like super sledges trained to spot patterns in massive datasets. They are trained to spot patterns in massive datasets, and they are the detectives who can effectively identify cancerous cells and tissues in histopathology images, uncovering every information that's often invisible to the naked eye of humans. So, the role of deep learning in cancer diagnosis isn't new, but it's heating up here with a special focus on convolutional neural networks for diving deep into histopathology images. Think of CNNs as experts in deep learning reading images, spotting features at different levels of complexity. This is where the magic happens. They've got super high accuracy, but they are like government chef. They need the best ingredients, which in our case is a huge dataset of histopathology image. But here's the catch. They need these images labeled by experts to teach them the ropes. Oh, and there's the boogeyman of overfitting, which means getting too specialized, which can mess with their mojo. But wait, ResNet, a kind of CNN, is our knight in a shining armor where there's a ton of data. It can help the model to run effectively from deep architectures. So, objective of the paper, we have three main objectives. But what's our battle plan, you ask? Here are the objectives. We are crafting a super powered deep learning model. Our target is to spot colon and breast cancer in histopathology images with laser accuracy. It's like we are arming pathologists with a superheroes magnifying glass to see what's going on. To make our model even more amazing, we are pulling out the big guns. We are using advanced machine learning techniques, including a trick called transfer learning with ResNet 152 model. This trick allows our model to find out complex patterns in images, patterns that show colon and breast cancer. We are on a mission to catch cancer early, increasing survival rates and saving money that's spent on treatment. And our third goal is our ultimate quest to revolutionize cancer care. We want to amp up the accuracy and efficiency of cancer diagnosis, which will lead to better outcomes for patients. Plus, we are all about improving access to healthcare, especially when in places where it is not as easy to come by. That's a game changer. Then, this is our proposed architectural view. We initially collect histopathology images of colon cancer and breast cancer. We feed it to a resident model and we train a binary classifier for classifying if the sample is benign or it is malignant. So, a pathologist can't infer much from this. So, to improve this, we will be using YOLO V5 model. Before using YOLO V5 model, we have to annotate each and every image that we have. So, we have to define the classes that we are going to annotate. The classes will be as follows. For a benign tumor case, we will be using the classes like crowding of glands, confined mucosa, mid-clear, nuclear and cell size variation. Polarity is almost maintained. Occasional mitotic figures, no invasion into stroma. When it comes to malignant tumors, we will be using the parameters like increased crowding of glands and loss of architecture, an increased number of mitotic figures, loss of polarity, severe variation in cell size and shape, also invasion into stroma. This will be annotated and will be trained by using a YOLO V5 model. And wait, it doesn't end here. To even more augment this, we will be using a linear regression model with morphometric values of cancers. So when we use a WSI, we measure the cell shape and size, which will be our morphometrics values. We have a huge collection of morphometrics. By using it, we will be feeding it to a linear regression model and we will be predicting the size and shape of a benign cancer and a malignant cancer, which will be a added advantage to produce our report. So the data set that we are using in our research is from Cancer Imaging Archive. Thanks to them for providing us the reliable data set. You can also find data set in Cancer Genome Atlas and you can also use Patch Chameleon dataset. I have displayed two different images at the bottom. The leftmost one is a adenocarcinoma sample, which is the cancer is positive. On the right side, we have a benign sample. This is where the sample is a negative cancer. There is no cancer. And then comes feature maps of convolution layers. Feature maps are like very important in training a CNN model, which are often done by convolutional layers. They extract all the features from the input image. You can clearly see that model gets to learn the patterns in each convolutional layer. In the first block, very less amount of data has been captured. Less amount of features have been extracted. In the second block, we have extracted a good amount of features. Almost the lobules, the oval lobules or round lobules are visible. In the third block, we can get to see all the patterns, but becomes little pixelated. Then comes linear regression as a supporting step. Alright, let's switch gears for a moment and talk about our sidekick, linear regression. At first, we went with a dataset that had just 10 parameters for cancer analysis, but we are not ones to settle. We bumped it up to 30 parameters, including some statistical gems like standard error and the worst values. Our model, well, it's like a bloodhound and it's hitting 92% accuracy for the training set and had an accuracy of 90% on the test set. These parameters are like the secret code to sort out different cancer types, making sure we are on the right path. But hey, every hero has their quirks, right? Linear regression loves the simple life but doesn't play well with outliers. It also thinks that everything in a straight line, which isn't always the case. So if you are going with linear regression for predictions, keep your wits about you. So comes the black box behavior of CNN, which becomes the main disadvantage here. So let us discuss how we handle this approach. CNNs are amazing, but they do not have a bit of mystery around them. They act like those black boxes where you put something in and you get something out, but you are not exactly sure how it happened. That's not always deal, especially in medical situations where you need to know how and why they are made a particular diagnosis. And and then there is the scratcher. When they make a wrong call, it's like trying to figure out a riddle without a clear answer. It can be frustrating, and when you are dealing with something as critical as cancer diagnosis, that's not something you want to mess around with. Plus, the world of healthcare, ethics and laws are big deals when the black box behavior of CNN comes into play. It can raise concerns about accountability and transparency. These are our parameters that I earlier told. In benign parameters characteristics, we use crowding of glands, confinement to mucosa, mild nuclear and cell size and shape variation. Polarity is almost maintained and occasional mitotic figures. When it comes to malignant tumors, we use increased crowding of glands and loss of architecture, increased number of mitotic figures. Also, the polarity will be lost, severe variation in cell size and shape. We will also find invasion into stroma. So earlier we discussed about the black box behavior of CNN. To overcome this, we will be using YOLO V5, which will make us explain why this will be a good approach for solving this problem. Alright, it's time to bring in the big guns. YOLO V5. It's not your average model. It's like a James Bond model of AI world, trained for real-time detection of objects in images and videos. It's super accurate and lightning fast. But what's the catch? It's trained to spot things in a single sweep. It's like it walks into a room and says, I've got this, and doesn't break a sweat even if the room's a mess. So YOLO is like a state-of-the-art object detection model designed for real-time object detection of objects in images and videos. They also use deep neural networks architectures, and they get trained on labeled image datasets. They produce good amount of accuracy, speed and performance. So YOLO follows a single stage object detection, uses a single stage object detection approach where we directly predict bounding boxes and class probabilities for all objects in an image in a single pass. This approach is constant with two-stage methods, making it efficient and suitable for real-time applications. So when it comes to cancer cell detection, the YOLO V5 model was trained on a labeled dataset of cancer cell types in histology images by us with a pathologist, achieving high accuracy in detection. It can identify and classify cancer cell images even when they are partially occult or cluttered environments. So when it comes to evaluation metrics, now how do we know if YOLO V5 is doing its job well? We can understand this by using a method called precision confidence curve. It's like a progress report that tells us how good the predictions are. It measures precision, which is like saying how many of my answers are right, and it measures recall, which is like saying, am I catching all the right answers? In healthcare, precision is a big deal, especially when false positive could mean unnecessary treatments. And then we can observe the graph. So when the graph gets more towards the right corner in precision recall curve, the more accurate our model is. Our model is around 90% accurate. So comes the output of YOLO V5 model. When a whole slide image is split into tiles and fed to the trained YOLO V5 model, our model will be able to detect cells in real time by our annotated model. The left image shows a inference on malignant sample, where we pass a malignant sample and we detect malignant gland under incorrect lumen. On the right side, we have a benign sample where we pass a benign sample and the model accurately picks up all the benign glands in the image and all the correct lumens of each gland. And then comes our conclusion. Alright, time to wrap this up. We are making cancer diagnosis a piece of cake with deep learning, especially by using CNNs. Our focus on colon and breast cancer is like having a Sherlock Holmes on the team, helping pathologists make quick and accurate diagnosis. We are not just throwing tech into the mix, we are making sure it's all practical in the real world. We are comparing our CNN model with other big shots in the game. We are tweaking things like architecture and using pre-trained model to make a difference where it matters. Uh, and then these are our references that we used while writing the paper. Finally, here I convey my sincere thanks to Deep Learning Laboratory, Department of Artificial Intelligence and Data Science, Ramco Institute of Technology, Tamil Nadu, India. Thank you.